Hello everyone, thank you for joining us today for our webinar. I am Liz Mueller, our Direct Marketing Specialist with Carus Corporation. Today's webinar is Controlled Jet Injection for High Mass Potassium Permanganate Delivery, and we have Mr. Drew Baird with FRX here with us today. Just a few items before we get started in terms of housekeeping. We do have all the phones muted to help cut down on the background noise. If you do have any questions, there is a feature where you can type in your questions. Please feel free to type those questions in as you think of them. You should have some time at the end of the presentation to go through those questions. If for some reason we don't get to a specific question or we do run out of time, we have the capability to see who question with your contact information, so we will be sure to follow up with you directly after the webinar. Also, we will share a PDF version of today's webinar, as well as we are recording this, so there will be a recorded version of this available that we will send out to all attendees. Most likely you can see that email from me either this afternoon or tomorrow. This slide here is just a look at our remaining webinar series. So we have Safety and Handling of Permanganate, where Mr. John Bull with Carus Corporation will present. In November, we have Mr. Bruce Marvin with Geosyntex Consultants will present permanganate and persulfate for in-situ chemical oxidation and water treatment applications. And then our last webinar for 2016 will be December 8th with Ms. Shanna Thompson with Geosyntex Consultants, optimizing a combined remedy using traditional and high-resolution techniques. If you're interested in attending any of those, please contact me. My contact information will be on the last slide of today's presentation, and I will get you registered. Also, here at the bottom, you can see webinars that we have already held in early 2016, where we do have recorded versions available. So if you would like any of those, please let me know. One additional thing we wanted to also note is we are participating in the Remediation Workshops throughout the United States this year, as well as FRX is. We have a few remaining in 2016 where Carus will be present. So on October 4th, Dr. Pamela Dugan with Carus Corporation will be presenting in Chicago, Illinois. On October 5th, Dr. Pamela Dugan will present in Indianapolis, Indiana, as well as Drew Baird, who's presenting today, will also be presenting at that workshop. Then we will also be present November 1st and 2nd in Raleigh and Richmond. And then we have Dr. Pamela Dugan again presenting November 16th in the Boston, Massachusetts workshop. These workshops are free to participants. So here is the website here at the bottom that you can go to get more information about these. These are half-day workshops where there's about 5 or 6 presenters at each of those in various locations. So this website will give you the remaining locations and the registration information if you are interested. And with that, I would like to introduce Drew. Drew Baird has over 15 years experience in remediation design and implementation, project and team management, field support services, and environmental consulting. He is currently Senior Geologist at FRX, where he leads the company's business development efforts and provides technical support on soil and groundwater remediation projects to clients in the United States and Canada. Prior to joining FRX, Drew was the East Regional Manager at Regenesis, where he was responsible for managing sales and technical support associated with the company's remediation products in the southeastern U.S. In addition, he served as Regenesis's internal technical leader for the remediation of fractured crystal and bedrock. Drew began his career in environmental services as a geologist for Rogers & Colcott Environmental in Greenville, South Carolina.
Liz, thank you very much. Very happy to be here today. We are broadcasting live from Carus Global Headquarters in beautiful Peru, Illinois. I'm here with Bill Slack, one of FRX co-founders, and we were fortunate enough to get a tour earlier today of the factory and laboratories where permanganate, both sodium and potassium, are manufactured. And if you're in the industry and in the area, it's a piece of history. You know, that the factory celebrated its 101st year this year. So I recommend coming up and getting a tour from Team Carus here. It's quite the education. So today we're going to talk about a set of methods and tools and processes that our company, FRX, uses to deliver a variety of remedial materials into the subsurface. We call it controlled jet injection. We are going to focus today exclusively on creating slurries, high solid slurries of potassium permanganate, and delivering those to depth discrete zones within the target treatment area. So controlled jet injection for permanganate slurries is what we'll talk about. And it's a little bit different from the ways that many of you may be using permanganate. I know most of you on the call are experienced at designing and executing permanganate injection projects, and I imagine a lot of those are utilized in higher permeability treatment zones, as what you see here in the dashed box. So you've got a permeable treatment zone. You can mix up a solution of either potassium or sodium permanganate and apply that to either dedicated injection wells or direct push points and get really high quality penetrative distribution of fluids through that higher permeability treatment zone, that target zone. But what about further up gradients or in these lower permeability zones like what we have on the right? These are zones where you can't flood in high volumes of permanganate liquids. There's just not enough injection porosity, not enough permeability to get good penetrative contact, good distribution. So let's zoom into that, and it'll give you a little, it's kind of a highlight of what we're going to talk about today. So we've got an injection boring penetrating into that low permeability formation. What FRX does with controlled jet injection is to create a series of sheet-like structures that are filled with solid potassium permanganate that are typically 25 to 40 plus feet in extent, in diameter, that are commonly a ½ inch in aperture or thickness. And we typically space those sheets 3 to 6 feet apart from one another. So how does permanganate distribute away from these lenses? Well, the primary mechanism is one of diffusion. Chemical diffusion of permanganate can create a reliable penetrative halo that in 18 months, 24 months can create a halo that's 4 to 6 feet in total thickness. And I'll show data from field sites that demonstrates this. So controlled jet injection does that with permanganate. Some of the presentation topics we'll cover are shown here. I'll give a little introduction or reintroduction, a very brief one to FRX, who we are and what we do. Talk about some key characteristics of potassium permanganate, RemOx S, as they pertain to mixing and injection, and then principles of controlled jet injection. Then we'll talk about some of the transport mechanisms via diffusion of permanganate, and that's been really well documented in the literature. We'll talk about some RemOx design and injection considerations, and at the end we'll have a Q&A with staff from both FRX and from Carus. And you're welcome to submit questions via the panel on the right. You can either type them in, or there is also a hand-raising functionality where you can pop your hand up and we'll be able to call on you. Before we dig into it anymore, I want to thank a few folks who helped put this together. First and foremost, Liz Mueller at Carus Remediation Technologies for organizing this, hosting us today, her and the staff here for welcoming us here in Peru. Mike Perlmutter at CH2M Hill, or CH2M in Atlanta, provided some information for this, as did GeoClean's Dan Bryant, and from Rogers and Paulcott Environmental, George Maloof provided some input as well. So I wanted to thank you all. So FRX, I'm only going to show 3 photographs. We're not a big company. We're a small, nimble company, and these are the 3 honchos, if you will. The co-founders are on the left side of the screen, Dr. Larry Murdoch and Dr. Bill Slack, who met at the University of Cincinnati doing research in the late 80s and early 90s on advanced soil fracturing. So that was EPA-funded research that they did there, published really widely. I think we're up to 22 plus journal articles and peer-reviewed publications covering some of the methods that have been documented. Doug Knight on the right side of the screen, many of you know, is our VP of Operations. So this is the core of the team, but not all of us. I don't have a photo of myself, but I'm part of it, as are Tammy Latham Knight and Dean Varner, Jesse Lowe, and Spencer Hallstrom, all of whom are on the call. So you've got all of Team FRX on the call with us. But this is our group. And what you can think of us essentially as an injection services company, but one that is very highly specialized and one that is founded in innovative approaches. So it's that sort of academic approach to developing technologies, and then good ingenuity, field ingenuity, to optimize the productivity and capacity in field. So what you see here in this photo is a custom-built early injection rig to mix and inject a variety of materials into the subsurface. When we first started, it was largely sand to enhance flow and fine-grained formations. We've developed a variety of tools to go into deep or hard rock formations, so difficult treatment zones. So the tools and methods to deliver a variety of materials to the formation, and then also some innovations to track and monitor what's occurring during injection. And this is going to look like a chart you've seen a lot of times, just pressure versus time, but this was very innovative at the time, measuring in real-time pressure. And we've learned a lot from just simply measuring this in real time. It tells you a lot. So that was a very innovative approach, as was surface deformation monitoring, which this is showing a total station and some survey points that have helped us over the years demonstrate distribution of injected materials at depth with changes in surface deformation. So it's a real culture of innovation, and everything I'm going to talk about today is based in good sound science and good field ingenuity. So that's us as a company, and really what we do, this next photograph is a trench that exposes some injections that Larry and Bill did early on, and it really exemplifies what's occurring in situ when we inject materials with controlled jet injection. And so what we've got here is a clay till soil that has been excavated to expose 3 lenses of sand. And this line up here near the top of the photograph is a string that's just been pegged into the sidewall to demonstrate horizontality. And each of these lenses was created at 3, 5, and 7 feet below ground surface. And a few things to point out of them. They are broad sheet-like structures that are sub-horizontal or horizontal in orientation. They go about 12 feet or so from the injection point, which was located on the left side of the photograph. They're filled with sand, and the aperture of that is about 1 centimeter. That's a centimeter scale that you see in the lower left-hand corner. And what you notice is just a lot of consistency to the form of the sand lenses. And that's really a hallmark of the work we do, is that consistency. And it's more than simply advancing a direct push point, exposing the formation, and then increasing the pressure on a pump until the ground breaks. It's a much more deliberate and controlled process to create this deliberate and predictable form of these lenses, in this case of sand. And that's what we call controlled jet injection. And we've used these approaches on over 300 projects all over the U.S., into Canada, Northern Europe, South America, and we've put in a variety of different materials. You see the dots are spread across a variety of physiographic provinces, so a variety of geologic settings all across the U.S. and Canada and Europe. So that's where we worked. This on the left is kind of an artist's rendition of what we do. The sand lenses that, again, are 25 to 40 plus feet in extent, a centimeter in aperture, usually spaced 3 to 6 feet apart from one another. Specifically for permanganate, we're going to focus on kind of 3 critical elements of this. One is the product itself, RemOx S or potassium permanganate. The other is the distribution or delivery mechanism, controlled jet injection to create these broad sheet-like structures of potassium permanganate in the treatment zone. And then the third part of this is a really critical element for distribution, is the chemical diffusion of potassium permanganate, or the permanganate ion, that helps create a penetrative distribution of permanganate in the target treatment zone. So this is sort of the three-legged stool that we'll discuss. And first, with the properties of RemOx S, you've got a granular crystalline solid that is dark purple, this beautiful dark purple, and has a metallic sheen to it, kind of this bronze-like appearance in certain views. It is a relatively dense solid, about 2.7 grams per cc for density of the particles. The bulk density, about 100 pounds per cubic foot, so similar to a silica sand. And solubility that I'll call relatively low in terms of the materials that we'll deal with in our industry. In the lab, about 6.5%, but that's, instead of solubility, call that thermodynamic equilibrium. I mean, that's as good as it gets. In the field, in the best case conditions, what practitioners typically see is 2.5 to 3% solubility. So a dense, heavy, low solubility material can present some challenges for handling and mixing the material. If you mix it with water, a lot of it's going to fall to the bottom of the tank, and some of it will solubilize, but not a heck of a lot of it very quickly. If you inject it into the formation with a thin carrier fluid, it tends to get strained out. The solids, whatever solids can go in, tend to get strained out, so that limits distribution and limits effectiveness. But there is a viable method for injecting a high solids content slurry. And that's the first step to control jet injection. We make a slurry. We make a viscous, high solid slurry that if we were putting sand into a gel, our gel and sand combination looks like this on the left. What we're talking about today is a potassium permanganate solid slurry that you see over on the right, dry and then put into slurry. On the left is a photograph, again, and you may be able to see sort of this thick, high viscosity character imparted by the high solids content. I'm talking 50, 60, 65% solid slurry in these solids, very high solids content to these slurries. So you make a thick slurry and then pump it into the ground. And anytime you pump something, any fluid, faster than what Darcys Law says the formation is going to accept it, you're going to make a crack. And that is it's a two-dimensional space. Call it a lens or a sheet or a panel. It is a two-dimensional space in soil or in rock. And what we do really well is to create that two-dimensional space in the target treatment zone. Keep it on target, keep it at depth where we want the material, and fill it simultaneously with the slurry. It's a single process to create the crack and fill it with the permanganate slurry. So that's a seamless process to do that. So in a nutshell, that is the process of controlled jet injection. What happens when we go out and excavate sites where we've done this process, we see this consistent sheet-like structure that's slightly concave upwards, like a saucer shape. In this case, this is Piedmont saprolite. So what you've got here is soil formed by the in-situ weathering, in-place weathering of crystalline bedrock. So all those different compositional bands, those different fabrics and textures are imparted by the relic bedrock. And if you were injecting a liquid, then you've got permeable zones that follow different contacts or follow these pods or bands of coarser grain material. That band in the middle is a lens of sand and a material called coke breeze that we injected as part of a research project last year. That's a centimeter scale there, so you've got this centimeter wide aperture filled with sand and coke breeze that extends about 25 feet in at a shallow depth. So the extent of this thing is about 25 feet. And note that it cuts across that relic fabric in the soil. And I don't want to suggest that geology doesn't matter, but one of the very important controls on distribution of these lenses is the in-situ state of stress, which favors sort of this horizontal or sub-horizontal orientation. Our processes with controlled jet injection help to enhance that by getting things started in a horizontal orientation, better ensuring a more predictable form. So we've seen this on a lot of sites, this form. So you upper left-hand corner is clay till in Denmark and a white seam of sand. On the right is Doug Knight mapping out some sand and coke breeze in that same trench that photographed earlier. On the lower left is Piedmont saprolite showing a sand lens in place. So we've seen this a lot. There are other ways. You don't have to dig up your site to see where these lenses go. There are other methods to evaluate distribution, but we've demonstrated that in a lot of peer-reviewed journal articles and publications, and our clients have shown it through a variety of presentations on the conference circuit. So it's pretty well documented. What that control helps us to do is to have a lot of precision on where we inject things, and that helps us to participate in some pretty innovative projects. I referenced Rogers and Colcott earlier. We participated in a project with them where permanganate was placed into a source area, a high concentration source area of TCE, as part of a combined remedy, and part of the combination was that down gradient for plume treatment, there were ISCO amendments added in a series of permeable reactive barriers, again created by controlled jet injection. And you see the proximity of that first barrier to the source area is close. Part of why we were able to employ this sort of approach is that controlled extent. We know where things are going to go out to a certain distance, and helps us provide more reliability and can really get, I won't call it surgical, but can be pretty precise on where we're able to employ different injection methodologies and different approaches. George Maloof from Rogers and Colcott has presented pretty extensively on this, has written a paper on the full scale, and if you're interested in seeing that as a case study, send me an email and I'll send you George's paper that was presented at Aqua Console in Copenhagen last year, and very well received. So that covers the principles of controlled jet injection, sort of a broad overview of those processes and principles. We're going to move on to the third part of this, which is chemical diffusion. So now we're going to talk about, we've established that we've got a proven and potent remedial solid in RemOx S placed with controlled jet injection into these broad sheet-like structures. Now how do we treat the zones that are in between the sheets? And that's where chemical diffusion comes in. And chemical diffusion of permanganate has been really well documented in the literature. From 2002, a team, including Amanda Struess from Colorado School of Mines, wrote a paper and published it in Journal of Environmental Engineering that explored this topic. Technical University of Denmark, some folks out of that group, published in 2007 in ES&T on that topic. So the science behind chemical diffusion of permanganate has been written about and covered well, and there's good technical information in there that you can use to apply to everyday site. The site that we were involved in that best demonstrates this is DOE's Portsmouth, gaseous diffusion plant in southern Ohio, and this is a cross-section showing geology, and I'll walk through some injection and then some confirmation borings and some of the investigation. But you've got a cross-section here showing shallow fill overlying a silty clay of fluvio-lacustrine origin, and a tight silty clay that also has some natural pathways, some natural vertical pathways. So hydraulic conductivity of that material is about 10 to the minus 6. It overlies some siltier and sandier zones. And what we did at this site was to emplace lenses of sand and then of potassium permanganate, of RemOx S, in these broad sheet-like structures. And we know the orientation of these things well because so many soil cores were put into these zones. And you see the location on the right shows the location of a lot of these soil cores, and the cross-section just goes through those. The soil cores we're down to about 18 feet BGS, and that's how we're able to map out the distribution of these lenses of sand and permanganate, which showed up really well in the core. So a variety of other tests were done as part of this. And this photo, it's a little grainy, but at the top core, you can see those ridges in the core imparted from just the direct push process. It's that modeling clay kind of look to it, and that's the natural color, that tan. And you can barely see the core in the bottom photograph, which is purple core. So that's been stained by diffusive penetration of permanganate, and you see the scale down there. What they did here was to go back and core periodically and take samples for a variety of tests. And one of those was redox. So on the left side of the screen, you've got a split scale in centimeters, and in the center at 0 is the permanganate fracture, so distance above and below in centimeters. And on the y-axis, you've got redox potential in millivolts. And you see that at and beyond the permanganate fracture or permanganate lens, you've got very high penetrative high ORP that then drops off as you get about 25 centimeters below and above the lens. And this is 10 months after emplacement of the lens in soil cores that are tested for redox, for ORP. So same vertical scale here, same permanganate lens in the middle, but what we're looking at on the x-axis is % reduction of TCE. And what was done here was 10 months after emplacement, took cores of soil and then mixed those with site groundwater that had about 50 milligrams for this groundwater 2 sample, was about 50 milligrams per liter of TCE. And you see the % reductions from the permanganate. And this is permanganate that hasn't been added to the samples above ground. This is permanganate in the soil core that's been mixed with contaminated groundwater. And they did it at 2-hour and 24-hour reaction time, and you see the complete reductions or complete destructions of high concentrations of TCE with permanganate. So a demonstration of diffusion through a variety of chemical measurements. And sort of the upshot of all this, you see core over here on the left from the site. The upshot of all this is that the sampling at various intervals, and it was time 0, 3 months, and 10 months after injection, they were able to mark out through purple staining and through this chemical testing and laboratory analysis a halo, a very well-defined halo that at the end of 10 months, you've got about 1.5 foot halo around the permanganate lens. And for further reading, this is published in '99 in the Journal of Environmental Engineering. So really effective demonstration of permanganate diffusion from emplaced lenses by controlled jet injection. It's been demonstrated at other sites too. This is from F.E. Warren Air Force Base in southeastern near Cheyenne, Wyoming. So these photos are courtesy of URS, and what they show in the middle on the left, you see that dark black purple granular permanganate that's about a week after application, and already you see a purple Kool-Aid halo coming off of that. These are CPT cores, so good wide diameter cores to demonstrate the distribution of of permanganate. So you've got this thin seam and then the broad halo in a fairly short period of time here. This is from about 40 feet BGS. 7 months later, there were additional cores taken, and you see a more penetrative distribution or penetrative diffusion of permanganate noted by the purple staining, about 28 inches after 7 months. And finally, I'll show a photograph from a different site. I showed a slide of a TCE treatment kind of plan view map showing permanganate ISCO and the source treatment. And we worked on this project beginning in 2011 and emplaced permanganate as a pilot. And then during the full scale, early on in the full scale, came back and took some sonic cores. And what you see here is Piedmont saprolite, so a silty sand of weathered in place rock, but it's soil. So saprolite soil, and on the right, that dark purple, that's where the lens of permanganate was emplaced. And 2 years after emplacement, that lens has migrated, or that diffusion front rather, has migrated about 2.5 feet. So that is where, I said at the beginning that diffusion halo can reliably extend 4 to 6 feet from each of these. Through these combined studies, we see pretty routinely a 1 to 2 foot diffusive migration of permanganate per year. And that matches pretty well with Fick's law. From just basic diffusion, that chemical gradient created by emplacing high concentration perm slurry and chemical diffusion can really drive a big penetrative halo or envelope to get destruction, get contact and get destruction of contaminants. So that kind of covers diffusion. So we've got a potent product. We're emplacing it by controlled jet injection, and then diffusion helps to get the penetrative distribution and fine grain formation. So we've done this type of work all over the place, beginning in '96, and we've worked in a variety of different geologic terrains, emplacing permanganate in the mid-Atlantic, down in the southeast, in the mid-continent clay tills, mentioned the site in Wyoming, and then in California. So we've worked all over the country in placing permanganate. Some of the statistics are that we've worked on about 28 injection projects involving potassium permanganate. This doesn't include our sodium permanganate work, but for RemOx S, that's about 28 projects, 18 sites in 12 states. So we've done multiple sites or multiple projects at different sites, which is why there's a discrepancy there between 18 and 28. And overall, over the years, we've injected over 1 million pounds of potassium permanganate RemOx S. And the project size ranges from about 6,200 pounds to over 450,000 pounds. So a pretty wide range from small or moderate scale to large scale injection projects. So those are some of the statistics for FRX experience with RemOx S. And we've been involved with a number of firsts. We're proud to have been the first injector of solid potassium permanganate. That was that Portsmouth DOE facility in '96. And one of the innovations from that site was that we developed and patented a unique mineral-based carrier fluid to suspend and inject the solid permanganate. So that was a really innovative development. Some of you may remember the Carus cycle bin. We just saw during our plant tour a few cycle bins out in the warehouse, and in 2003 we were the first group to use the cycle bin, and that's an enclosed bulk permanganate shipping and handling material or apparatus. And what was important about it at the time is that it allowed us to more safely mix and handle permanganate. So instead of using bags and buckets, we could move up to bulk systems. So it helped a lot with productivity and safety. And then we, in 2009, we were the first to apply solid permanganate in bedrock. That was a Superfund site in eastern Pennsylvania, and has been presented at various conferences. So that was another first there. So we've done some firsts with permanganate, and for this kind of last leg of the presentation, what I want to talk about or give you some ideas about how much and how quickly, and some design rules of thumb that you could think about on some of your projects. So again, we've got lens-like features of potassium permanganate, of RemOx S in the subsurface. Each of those lenses routinely holds 1,000 to 2,000 pounds of RemOx S. We are capable of delivering much larger quantities per lens. We've delivered smaller quantities per lens, but a very typical lens is 1,000 to 2,000 pounds of RemOx S per sheet, per lens. And remember, that thing is only a centimeter in aperture or half-inch in aperture and reaches out 30 feet or so. So we fit a lot of that into a small space and a small volume. The emplacement time for each of these lenses can be measured in minutes. 10 minutes, 20 minutes. This is not hours to create each of these. It's rapid emplacement. So you can measure that in minutes. And at the end of the day, we've emplaced what can be measured in tons of material. And there are 3 projects that highlight that. One in the Dallas area in 2002, where our average production was 4,300 pounds of solid permanganate injected per day. For the South Carolina side, I highlighted a couple of times. Production rate was almost 7,000 pounds per day. And then last year in Central California, about 7,200 pounds per day. So lots of mass in a relatively short period of time is one of the hallmarks of controlled jet injection. In terms of dosing, I want to give a quick sort of comparison on dosing as a way to illustrate just how powerful sodium permanganate can be as a solid. And a lot of you have worked with liquid permanganate, sodium permanganate, and a 40% solution of sodium permanganate is a powerful oxidant. It contains 3.8 gram moles per liter of permanganate ion. Well, a 16 pound per gallon slurry of potassium permanganate has about double the number of gram moles per liter of permanganate ion. So it's just a really potent mixture that we can deliver into the subsurface. And our delivery, it involves relatively low volumes. So just looking at a comparison of volumes, we're taking a super sack in the upper left-hand corner. That's a 2,000 pound super sack of RemOx L, and blending that into a thick slurry that measures 16 pounds RemOx S per gallon of slurry. So a good thick viscous slurry. The volume of that slurry is about 213 gallons. So you can easily fit it in an IBC tote. Not that you would, but if you wanted to, you could put it in the tote and have a lot of room to spare. So that's one super sack into 213 gallons of a viscous slurry. Contrast that to if you were going to take 2,000 pounds of RemOx S and mix it into a 3% solution, which is fairly common solution percentage. You're not going to be surprised that you need a lot more volume. You're going to need a lot more totes. That is equivalent to about 8,000 gallons of liquid, or 29 totes, equivalent to about 29 totes. And as I started out the presentation, I acknowledged that these permeable treatment zones, you all have experience, many of you have experience mixing and injecting permanganate solutions, including RemOx S solutions, and targeting these permeable zones. A very effective way to flood in and get penetrative distribution of a liquid. What we're talking about doing is targeting tougher zones, fine-grained, bedrock, more challenging lithologies. Could be a permeable zone if you wanted to do it that way, but we're doing it with considerably less volume and relying more on diffusion to help carry out the rest of the distribution scheme. So a few rules of thumb, and then we'll get on to the Q&A part of this. Because we're able to emplace these structures that are 25 to 40 plus feet in extent, in diameter, we routinely have injection spacing, the points, on 25 to 35 feet. The lens spacing is usually 3 to 6 feet, and that seems to be a good number based on diffusion rates. But if you have a brownfield site that you need to clean up more quickly, then it just means putting those lenses closer together if you want to approach it with permanganate. And then that diffusion halo, we showed some data illustrating the speed of diffusion. You can make a big halo in a relatively short period of time. So here's some of our equipment. We've got mixing tanks on the left, our injection apparatus in the middle, and a pump hoist truck to go do some deep downhole work on the right. Light, mobile, reliable equipment that we pull all over North America and can be at a site in a short number of hours or days, depending on where we are and where you are. So where clients typically call us, where FRX fits in really well to these injection projects involving permanganate, is when you need to get in a lot of RemOx S into a small volume, so deliver a high dose rate to the target treatment zone. We've demonstrated and documented distribution certainty through a variety of outlets, peer-reviewed publications, presentations, a lot of good technical scientific work to demonstrate distribution, to give you more certainty on where these materials are going to go. And then when you're working in challenging geologic settings, a tight overburden or heterogeneous overburden or a really thick treatment zone, bedrock sites from mudstone to diorite or granite, these are environments where FRX has some unique capabilities. And we would welcome the opportunity to take a look at your projects where you're evaluating permanganate and see what kind of ideas and resources we can bring to bear on the project. When you're evaluating the site, the information that we need is pretty simple stuff. Number one is, what's the drilling method to get to the target treatment zone? Is it direct push, or is it some other drilling method? Where is the site located? How big is the target treatment zone? How much permanganate do you want to try to deliver that to that zone? And then the geology and hydrogeology of that target treatment zone. So as we move on to, we've got about 20 minutes or so for questions. As we move on to questions, I'll bring up the contact list, both for Team Carus across the globe, and then FRX. Many of you have worked with Bill Slack and Doug Knight and Larry Murdoch over the years, and you're also welcome to contact me. So we've got a number of questions that have come in from participants, and we'll start the Q&A section right now, and feel free to add more with the chat functionality.
Great. Thank you, Drew, for a great presentation. As he mentioned, please go ahead if you do have any questions, type those into the questions and answers section, and we'll have plenty of time to get to these. Also, just as a reminder, we will send out a PDF of the presentation as well as this is being recorded, so the link to the recorded version as well to all participants either this afternoon or tomorrow. So with that, we have a question that came in. How tight of soil can you inject into? Can you inject into a tight clay? And how effective is the diffusion of permanganate into that tight clay?
So tight clays are a place where FRX first began our work. So we have lots of experience in some of the tightest, most challenging formations. I showed an example from that Portsmouth site that was 10 to the minus 6 centimeters per second hydraulic conductivity. The hydraulic conductivity at that site in southern Ohio, where you had kind of the worm's eye view of the lenses, 10 to the minus 7 centimeters per second, I believe. So very, very tight clays. We can create these structures very reliably in very tight clay. As far as diffusion goes, I encourage you to email me for some of the references on diffusion, but that mechanism is very reliable, and it's been demonstrated and documented really well in the literature. Not just the study that I showed from the Portsmouth DOE facility, but Colorado School of Mines, Technical University of Denmark have illustrated those concepts in the literature really well. So it is a proven distribution mechanism for permanganate ion, which is what we need to come into contact with our target contaminant. Great.
And another question is, do you ever see manganese dioxide clogging the formation?
This is Bill Slack. We're aware that that can be a significant mechanism. The action here is placing permanganate, potassium permanganate is placed as the lens, and then it dissolves at the concentrations that you would typically use if you were applying it as a solution. So it's going to have similar sorts of impacts. I know that some of the work we've done, the slurry that we have injected has been a mixture of sand and permanganate with the idea that the sand would assist in keeping or minimizing the consequence of the manganese dioxide precipitation in the gap of the lens itself. So we've addressed that issue. Regarding any of that happening outwards somewhere out in the formation, I think it's more of a question I'm going to throw over to Liz and let her answer that one in terms of what Carus knows about that.
Sure. Do you want to?
Sorry, I had to run across the room. This is Kelly Frasco, and typically once you have the permanganate dissolved in groundwater, we don't necessarily see issues too much of manganese dioxide clogging the aquifer, but it really is how you design the site. I mean, if we have a high background demand site, you're going to, and high contaminant concentrations, you're going to see a higher chance of having manganese dioxide actually plug the aquifer. But honestly, when we look through the literature and when we speak with most of our customers, we don't hear of it being an issue too often. Where we do run into problems is if you're injecting into a well where you have, once again, those high contaminant concentrations and a high background demand, and you're injecting a high concentration of permanganate, it's kind of like the perfect storm, and you're going to end up with manganese oxide in that well. If you have further questions, once again, we have lots of references that we can send along, so feel free to reach out to us, and we can get those references over to you.
Great. Another question, how do you determine the amount of RemOx to inject? Based on NOD or based on contaminant amount of lenses per soil volume?
Well, ultimately, I'll start with this, Bill, and then you can add some clarification. Ultimately, the dose rate of the permanganate, the amount of permanganate you need to deliver to the target zone is going to be based on the combination of natural oxidant demand and the demand from the contaminant. So some of the sort of typical investigative and analytical methods that you would use to determine how much permanganate you need, you would continue to do that as normal. The place where controlled jet injection and FRX would come into the design phase is helping with point spacing and lens spacing. And so there are some rules of thumb and some calculated, ranging from rules of thumb to calculated results for amount of material per lens, for spacing between points. It can be again, based on simple rules of thumb, or we can get much more analytical and quantitative to assist with that part of the design. You have anything you want to add to that, Bill?
Nothing in particular. The NOD does govern, as you said, the amount of material that needs to go in to take care of the issues.
Okay. Right. And then another question, you mentioned about the typical volumes per lens. What is the maximum potassium permanganate quantity that can be injected into those lenses?
Yeah, so I introduced or suggested presented in the content of the webinar that typical lenses are 1,000 to 2,000 pounds, that we've injected much larger quantities than that. And Bill can probably recall what the sort of maximums would have been over the years.
I think the maximum amount of solid material that we've injected into soil is probably something on the order of 10,000 pounds. I think it was a sand situation, sand having similar sorts of density and specific gravity to permanganate. We give similar sort of scaling, but the real critical issue is the matter of the return you're getting for your effort of trying to put more material in one place. There's a couple things that are going to go on. First is that the size of that lens is going to expand as you inject more material into it, but it starts to expand, the extent expands less quickly than you might think, and so in order to double the size of the extent, maybe you need to put in not just 4 times as much stuff, or 8 times, or maybe 16 times as much stuff, and so you start having to commit a lot more effort to get a larger extent. There's also issues with where of reliability of where the form is going to propagate, and the larger it gets, the greater the chance is that Mother Nature is going to rule where the limit of this lens is, and we start losing our degree of certainty about what we're doing, and we don't want to do that because the objective is to put this treatment material at the right place in the right dose to get the job done.
So it's a 1,000 to 2,000 pound lens. We have a lot of certainty on where the tip of that lens is going to be when we finish pumping. We can keep pumping more in, but the certainty decreases with distance.
Okay. And then another question, how long does the RemOx last in soil in general?
You want to, Team Carus, want to start with that one, and then we can talk about some of our Kelly's going to come over again and answer the question.
So that's a great question, and I think it's a question that we get asked quite regularly. How long does permanganate persist in the subsurface? And permanganate doesn't auto-decompose, so it's going to persist in the subsurface until it comes into contact with something it can oxidize. So it really does depend on that background demand that we've spoken about. It depends on your starting permanganate concentration, your contaminant concentration. So there's quite a few factors that play into that. We've seen sites, some of our customers, they want to go in with the intent of hitting it hard, if you will, and going with higher concentrations. For those sites, we've seen permanganate persist in the subsurface for years. There's other sites where, it only persists for a few months. So there really is quite the substantial range. I don't know if anyone from FRX, okay, feel free.
Yeah, so the way that we're emplacing this is a high solid slurry. You've got a lot of permanganate mass in a small volume, and it dissolves and diffuses slowly. So the longevity of these in-place lenses is measured more on years, oftentimes, than in months, because we're putting in such a high concentration into a thin little lens that dissolves and diffuses slowly over time. So that often is a design criteria, is that the plan, if you will, the remediation approach, is to have a persistent permanganate source for a period of years, and these methods can help ensure that sort of persistence and longevity.
Okay. Are there depth limits to these applications?
Not yet, not depth limits yet, but we're sort of pushing the envelope right now, I guess. I'll let Bill chime in. Our deepest work to date has been about 200 feet BGS, but that's going to change beginning week after next, when we're going to go closer to 250 feet BGS. So one of the trends in the work that we do is to work deeper. That's been a trend over the last few years. So you want to talk, Bill, about some depth?
Sure. We certainly can go to the other end of the spectrum too and talk about how shallow can we go.
Sure.
And the physics of creating these lenses, these two-dimensional shapes, are not constrained by depth so much. Certainly on the shallow systems, the competition is the backhoe, which can easily remove the top foot, 2 foot, 3 foot or so, and take it away and more effectively manage it than any injection scheme of anything. I think the shallowest work that we do on a routine basis is probably somewhere in the 5-foot range, although in the University of Cincinnati days, we played around trying to see how shallow we could go, and it was certainly somewhere in the matter of 1 foot, 6 inches, something like that. That's all truly ridiculous, just university things to do. In terms of depth, I mean, the general exercise of applying pressure and creating a crack is the same thing that the petroleum industry has been doing for about 7 decades now under the guise of hydraulic fracturing, and that the deepest record on that is probably somewhere well below 20,000 feet. So there's plenty of opportunities to take on there, and depth's not a limitation here.
Okay. And then there was one question in regards to Europe. So I don't know if, Phil, you just kind of want to briefly talk about your global reach from an FRX?
We've done work in Northern Europe, and our approach is to couple with some practitioners, local practitioners, and with their help in characterizing the site and providing logistics support for getting there, implement technologies on the site. We've got some very good friends in Denmark that we can work with. We have some friends in Germany that allow us some access there. So we can get to Europe and perform some of this work, although we're going to have a lot of phone calls about it.
Great. Well, with that, we want to thank Drew and Bill again for this great presentation, and thank you everyone for joining us. If you do have any questions, Drew's contact is here, as well as our Carus representatives. Feel free to contact any of us. If you're interested in joining any of our webinars, please let me know. We'll be happy to get you registered. And be on the looks for the PDF of today's presentation and the recorded link. Thank you.